This is problem 17 of the QHack 2023 Quantum Coding Challenges, and this one is entitled A Halfway Decent Photocopier. Now, in this problem, what we're told is that there's two parties. One is Zenda, the other one is Reese, and Zenda wants to send her state psi to Reese, but they cannot apply any gates in between the two qubits that they have. Now, what they do tell us is that Zenda and Reese share a bell pair. So then we need to figure out how can we construct this block's Z, copier, and printer to transfer the state psi from this qubit all the way down to this qubit. And as you can see here, even though they cannot apply any gates between their two qubits, we are given two auxiliary qubits here where we can apply some operations to connect things all the way from here at the top to the bottom. Now, when we see something like this, where we're trying to transfer a state to another party using a bell pair, well, that resembles the typical quantum teleportation protocol. So let's review that and see if there's anything there we can rescue to solve this problem. So in quantum teleportation, we want to do exactly the same as what is described in this problem. Two parties, in this case we're going to call them Alice and Bob, and they share a pair of entangled qubits. Here are the second qubit and the third qubit, the ones that they're entangling. And then Alice is going to transfer the state zeta all the way down to Bob. And the way it works is by using the circuits shown here, right? So the first thing we do is, if zeta is an arbitrary state, alpha 0 plus beta 1, well, the first thing we have here at the beginning, this psi 0, is just that zeta, and then the pair of qubits that Alice and Bob have are initialized at 0, 0. Then when we entangle those two qubits, well, we just have the same state zeta, and then an equal superposition of state 0, 0 and 1, 1, right? So this Hadamard gate here with this CX gate just entangles those two qubits, and that generates this bell state. Next, what we do is we measure the top two qubits, so Alice's qubits, in the bell bases. Now, to transfer her qubits to the bell bases, what she does is she applies a CX gate followed by a Hadamard gate. And the state that we end up with here, denoted at psi 2, is of the following form. So here we have grouped, we can factor things out, and here we have grouped Alice's qubits here first, and then the last qubit, now the one that Bob has this coefficients alpha and beta, and as we can see here, what Alice has is state 0, 0, state 0, 1, or state 1, 0, or state 1, 1, right? And in a superposition with a state that Bob has that resembles very much the state zeta that we want to transfer, except that in this case is identical. In this other case, the bits are flipped. So here we have a 1 and here the 0 instead of the other way around. Here the face is flipped. And in the last one, we have both a face flip and a bit flip. So if Alice performs a measurement on her qubits, well, she knows that if she gets a 0, 0, she can just communicate to Bob that he doesn't have to do anything to his qubit. If she measures 0, 1, she can communicate to Bob that he needs to apply an X gate. And the way we would do that is, well, if this second qubit here is 1, which means this qubit is 1, we can apply a control X on Bob's qubit based on the measurement result from Alice. Now, this doesn't have to be, a direct wire there. Alice can just pick up the phone and tell Bob that he needs to apply an X gate to his qubit because that's what she measured, right? And then if she measures 1, 0, that means that Bob needs to apply a Z gate to his qubit because he needs to invert the phase, right? And if she measures a 1, 1, she needs to tell Bob that he needs to apply both a Z gate and an X gate. So basically, that's why this measurements on Alice's qubits are conditioned to apply those gates on Bob's qubit, right? So if Bob does that, then we can see here that with 0, 0, he does nothing, applies identity. So Alice gets 0, 0, and Bob gets the state zeta. If Alice measures 0, 1, she tells him to first apply an identity followed by an X gate. So then he gets zeta again. Then if she measures 1, 0, apply the Z gate, and then just an identity, right? Do nothing. And then if she measures 1, 1, then Bob needs to apply a Z gate followed by an X gate so that he can recover, in all cases, state zeta. Now, if we run this protocol over and over again, we get each of these possible states with probability of 1/4. But in Bob's case, he always ends up with the correct state. Now, let's take a look at the problem that we're trying to solve here, right? So if we look at this, here we're given this circuit where Zenda and Reese are sharing a pair of Bell states here, right? So we're preparing a Bell state at this point, which is very similar to what we had done here up to psi 1. And then we need to figure out what Zenda needs to do here. Well, if we follow the same idea of quantum teleportation, she can just do that conversion of her qubits to measure in the Bell basis. So this block Z could be maybe applying this CX gate followed by a Hallamar gate. And then after that, at this point, forgetting about this auxiliary qubits here, we would have a state of this form 3, right? So we know that Alice has a superposition of this all possible states 0, 0, 0, 1, 1, 0, or 1, 1. So then in this photocopier, just apply CX gates from this point to this point and from this point to this point to kind of copy that down here to this auxiliary qubits. And then on the printer side, Bob could do, or in this case Reese, could do something very similar to what we did here with the measurement and the application of the Z gate and the X gate. So how would that look like? So basically we have the preparation of the Bell states here, the change to measure in the Bell basis, then we copy Alice's qubit from here to the auxiliary qubits using CX gates. And then here, this is almost as if we had performed that measurement, right? Because here we have all those possible solutions that Alice had measured in the case of the conventional quantum teleportation. So all we need to do is apply conditional quantum gates of the same form that we have in the conventional teleportation protocol. So if we now look at this state psi 2, which would be around here, right? So before using the CX gates on this auxiliary qubits up to this point, we had said that we had the same as what Alice had in the traditional teleportation protocol before measurement. So if you notice this state psi 2, that looks exactly identical to what we had before, but now in green I have added this additional qubits, which is just basically the CX gates pretty much copying these states that Alice has, or in this case Zenda has in her possession, right? So all the CX gates are doing is just copying that to those auxiliary qubits. And then if we look at what happens after applying this condition Z gate and conditional X gate, well, that's just going to perform the same thing that classically conditioned gates Bob had in the traditional teleportation protocol we're doing, right? So if we have 0, 0, nothing happens. If we have 0, 1, then we need to apply a bit flip. So that's what this CX gate is doing here. If we have 1, 0, then we need to apply this Z gate. And then if we have 1, 1, we need to apply both of them. So you can see here that this is almost identical to the conventional teleportation protocol, but all we've done is just use a pair of auxiliary qubits to make copies of what Zenda had on her qubits, and then quantum control gates so that Bob can apply the corrections to recover the state zeta. So let's go ahead and take a look in PennyLane how this will look like, right? So as always, the first thing we're going to do is import PennyLane and NumPy. Then we're going to define our device. And here I'm using the wires that are given in this problem. So Zenda has qubits Z0 and Z1. Then Reese has qubit R1. And then these are the auxiliary qubits S0 and S1. And then in this problem, this alpha, beta, and gamma are parameters that are given to us to prepare this state psi using a U3 gate. So that's the first thing we're going to do here, is apply that U3 gate. Then we need to define the circuit that generates the bell pair that Zenda and Reese share. So that is just basically a Hallamar gate followed by a CNOT gate. So Hallamar on qubit 1 that Zenda has, and a CNOT gate between qubit 1 from Zenda and Reese. Next, we're going to apply that CX gate and Hallamar gate on Zenda's qubits. Then the CNOT gate from Zenda's qubits to that auxiliary qubits, that's what in this diagram is called a copier. And lastly, the conditioned Z gate and CNOT gate that goes from each of the auxiliary qubits to Reese's qubit. And then in this problem, we're asked to return some expectation value on some observables on Reese's qubit. Okay, so with that, we can now draw our circuit. So here we have the unitary that prepares the state that we're gonna transport. Then we apply the gates that generate the bell pair between Zenda and Reese. Then that CX gate and Hallamar gate on Zenda's qubits. Then the CX gates that copy from Zenda's qubits into the copier, which here are shown at the bottom. And then that conditioned Z gate and X gate on Reese's qubits. And finally, calculating the expectation value of some observable that we're given. So now to check our results, let's take our circuit and then pass some of the inputs that are given in this problem. The first input that is given to us is alpha, beta, and gamma of 1, 1, 1. And that gives an answer of 0.82135. And if we go down here to the solution, we can see here that for that input, we get 0.81735. And then the next input is 1.2, 1.3, 1.4. So let's pass that as an input. Let's print that. And then here we get 0.9604. And here we can see that that's the expected answer for this problem. So that's it. I hope this was clear enough. And as always, let me know if you have any questions.